We're drawing magnetic fields. What do you say about that? Hey there. So we're drawing magnetic fields here. Magnetic fields are commonly referred to as B fields, and I'll typically write that as like a script B. I don't know. B pops up in my name a lot, so I'll have my own little way of writing it. And it has units of Tesla, named after Nikola Tesla in the 1960s, I believe. That's why the car company went with the name Tesla for Nikola Tesla and the idea of electricity and electric cars. But instead of going with electricity for Teslas, we went with B fields with Teslas. And some of the work we did, because these are two ideas that go very, very well together, electricity and magnetic fields. We're going to be drawing them though. So if you remember back when we did electrostatics, we were drawing electric fields. Now we're going to draw magnetic fields. And there are a few different rules that go in with that, and something really weird. When we drew electric fields, we could just say normally they were like left, right, up, down, and call it a day. But magnetic fields, they get a little weird with some of the math that happens, and we actually need to go in 3 dimensions, X, Y, and Z. Now, since this might be the first time you're ever working in 3 dimensions, let's talk about them real quick. We've got 3 dimensions, X, Y, and Z. Those are axes, and we can have positive and negative of each of them. So if we've got some 3-dimensional axis set up like this, and we can go X, Y, and Z in any of the dimensions, we actually have 1, 2, 3, 4, 5, 6 directions we can go, because each of the 3 axes have a positive and a negative. So here, you see we can go left, right, up, down. Those are X and Y axes. But then we can also go in or out of the page. This is like the Z axis. And this is how we're going to try to draw 3-dimensional things on a 2-dimensional surface. Because it's kind of hard to draw like out here and be like, what are you pointing at? Like, I don't know what I'm pointing at here. This is hard. So instead of trying to draw these 3D kind of shapes, we're going to stick to 2D, but we're going to give ourselves a third way of doing this. We're going to say in and out. And for in, we're going to use an X or an X with a circle around it. And for out of the page, we can draw a dot or a dot with a circle around it. And sometimes students find this a little hard to remember, but I tell you what, when I was a wee young lad many millennia ago, my grandmother taught me B fields, and she made me this Robin Hood hat. Robin Hood was one of my favorite characters growing up as a child. I watched Disney Robin Hood all the time with those foxes. I watched Kevin Costner's Robin Hood, Prince of Thieves all the time. I loved it. And here's how you can remember this via Robin Hood. Robin Hood's weapon of choice is a bow and arrow. And let's specifically look at the arrow here. If you were shooting an arrow into a piece of paper or a board or a wall or whatever, the last thing you see as this arrow enters is these fletchings, those little feathers at the back end of the arrow to stabilize its flight. Those little fletchings kind of look like the X. So if you're driving an arrow into a page, you pull back that arrow, you let it, you've driven it in, you see the fletching, it's gone into the page. Now every once in a while physics gets angry and physics fights back. So if physics fires back at you, well, right before it zoomps you in the eye, the last thing you're going to see is just a tiny dot coming at you. You're just going to see the tip of the arrowhead, and that's going to be it. Okay, so out of the page is that arrow's coming back at you. Okay, so these are our 6 ways that will designate direction with B fields. And let's just figure out how we start drawing them now. So let's just draw for ourselves a basic bar magnet. So this is just a rectangle with a north and a south end. Now traditionally what you'll see, and you'll see this on web pages, websites, books, it's traditionally said that magnetic field lines go away from the north and towards the south. So they look something like this. And they're symmetric on both sides. So we'd have this kind of like backwards bean shape. And they'd be technically everywhere. Okay, and their strength can be designated by the density of the lines, just like with electric fields. But this isn't exactly true. Okay, remember, there are a bunch of electrons inside this material, all pointing in the same magnetic spin direction for their domains, which means that these B fields, they end up being closed loops. They actually come back through the bar magnet like this. So while we can say that a B field does point from north to south, because as we see on the outside, all of these lines are coming from the north end and pointing towards the south end. When we get inside of the magnet, we just close those loops out and we bring them back to the north, okay? So that's kind of what's going on there. And this isn't probably the best diagram of this. In reality, the curves would probably look a little bit more if I had to draw this. The curves would look a little bit more. I still did a bad job. In a real life example, they'd look a little bit more like this. But generally, when we're looking at it, we care mainly about just the edge pieces, okay? So that's just something to keep in mind whenever you're drawing B fields for north to south. They go north to south, but be careful with the insides there, okay? Now, when we think about magnetic fields on Earth, we normally think about compasses, because compasses kind of point us north. So if you have a compass, we call the north end of a magnet the north seeking end, and that's what this little red and white thing on a compass is. This is the north seeking end of a compass. So this red spot will point north. And if we look over here, here's our little compass here, it's pointing north. Now, this is kind of a misnomer then, because while it's pointing north geographically. It's pointing to like the North Pole, so to speak. But that's not really what it's pointing to. The magnetic pole is not at the North Pole. The magnetic pole is offset by some amount. And same with the South Pole. Now, if this magnetic field is pointing this way, and this is the direction the compass aligns, and we just said magnets generally point from north to south, that means this up here is actually my south magnetic pole, and this down here is my north magnetic pole. So geographically, this is my north, and this is my south. But magnetically, the north magnetic pole is in the southern hemisphere, and the south magnetic pole is in the northern hemisphere. So that's a little weird, and it just has to do with how we define things and how things are pointing, okay? One other weird thing that pops up due to the fact that these magnetic poles aren't exactly lined to the geographic poles is the following. Let's say you're an Arctic explorer and you're looking for the North Pole, okay? If you've got some compasses with you, those compasses are pointing to this geographic pole. So if you're right here, you're not going to get a reading that tells you to walk this way. You're going to get a reading that tells you to walk this way, which is a little weird. Because of this, whenever you get around 10 degrees up here, like that, I think it's around 10 degrees, it might be 20. But whenever you get pretty high, either into the north or the southern hemisphere, you actually, if you're using a compass, need to make an adjustment to calibrate the fact that this magnetic pole and the geographic pole are at different positions. And if you don't, you're going to get lost and die. Okay? This used to be an issue with planes as well. But now that we've got kind of GPS and satellite positioning, it's gotten easier for that. But yeah, this used to be a major issue for not just planes, but adventurers as well. So be careful out there, all my adventurers within the intergalactic, as you're going into your north and south poles there. Okay? But that's just kind of how we do some B fields there. It's nothing too crazy drawing them out. The real thing to recognize here are these 6 directions, left, right, up, down, into the page and out of the page, because we'll need them whenever we go ahead and start running our right-hand rules, which are coming up in the next video and an optional video after that for what's known as the vector cross product, okay? Because I smell it. I smell it coming. The big cheese is coming soon, and this big cheese is going to be fun. But until we get there, for right now, we are finished. Y'all take it easy. Have a good one. Adios.